Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Oh, I didn't bring the prototypes down.
Thanks. Sorry we're getting started a little late, but welcome back to the second Microsoft installment of the Microsoft and UW Accessibility Seminar. And this week's speaker is going to be Scott Saponis, who has both UW and Microsoft roots. So he just finished his PhD in the computer science department at UW over the summer, and he just joined Microsoft Research this fall. So this is a good way for everyone to get to know what Scott's been up to and what he might do next.
Thanks, Mary. All right, I actually left the prototypes for this in my office, so at the conclusion of questions, I am going to sprint up to my office and sprint back down again, and then you guys can all see and feel what these things actually look like that I'm going to talk about today. So you have that to look forward to after my questions, or after questions at the end of the talk, or feel free to interrupt me as much as you guys want during the talk. So what I was going to talk to you guys about today is some of the work that we did the last couple of years on optically sensing tongue gestures for computer input, or tongue-computer interfaces. It sounds a little wacky, but it's kind of interesting stuff. This is work I did here at Microsoft Research with Desni Tan, who's also here at MSR, and my manager here, as well as Dan Kelly, who is a master's student in the EE department, who's graduated now, and Babak Perviz, who's a professor in the EE department at UW. So a lot of the work that I do, oh, look at this, job talk leftovers. A lot of the work that I do is trying to figure out how we can utilize some of the untapped bandwidth of the human body for computer input. So like my dissertation research was focused on muscle-computer interfaces, so how we can do things like from the surface of the skin, detect the electrical activity associated with our muscles, so we can do things like interact with the computer using finger gestures, but without actually having an input device in our hands. And the work that I'm going to talk to you about today is actually in the same theme. But here, the untapped bandwidth we're going to try to utilize is our tongues. So it turns out our tongues are a pretty interesting and unique part of our body. There are only muscle that's attached at only one end. If you move your tongue around in your mouth, you can feel that it's pretty dexterous. It also has, sensors on it. You can feel each one of your individual teeth. You can manipulate it pretty precisely. You use it to do things like manipulate food in your mouth. But you also use it in things like speech very precisely without even really thinking about it. So our tongues are super powerful. But you'll notice that when we interact with computers, we don't utilize any of that part of our physiology or our brain. One of the reasons why I'm interested in looking at tongue-computer interfaces is for use for people who have traumatic brain injuries, spinal injuries, or diseases of the nervous system like Lou Gehrig's disease. So as you guys know in this accessibility class, you guys have probably talked about at least a few of these things before, but there's a variety of interfaces out there for people, for example, who are quadriplegic. Things like sip and puff switches, voice recognition, as well as non-linguistic voice, brain-computer interfaces, head tracking, eye tracking. And these all have uses that are pretty good for a bunch of different applications, things like voice recognition for doing text-to-speech and dictation. But they're also pretty limited in how many bits of input they have. And for somebody who doesn't have any motor control, it's hard to do things like manipulate a motorized chair, for example, with these modes of input. So instead, like I said before, what about instead trying to use our tongues to control it? Well, it's not exact. We thought, why not use the tongues, because for most people who have like a spinal injury or brain injury, they usually tend to still have full control of their tongues. But how do you put some kind of computing in the mouth so that you can actually sense how your tongue's moving around? It's not entirely obvious at first. Before I get to how we did it, there's actually a few different pieces of work that people have done in the past looking at tongue movement, and there's kind of two different classes. So one of them is taking your tongue and kind of using it like you would use your finger to touch like a button on a keyboard or a mouse or a game controller or something like that. So here what people have done is basically put something that is the equivalent of a directional pad or a number pad in your mouth, like against the roof of your mouth. And then you can kind of imagine curling your tongue back and then trying to press those buttons for like on a number pad if you're dialing a phone, or a directional pad if you're trying to control something. Then the other main approach that people have done is augment the tongue in some way, in this case with a magnet, and then put sensors on the outside of the mouth to try and detect the movement of that magnet that's affixed to your tongue, and then be able to use your tongue movement in that way to control a computer. So we don't really like either of these approaches. The reason we don't like the approach on the left there is because it's not very comfortable to curl your tongue up in your mouth and be constantly pressing against things. That's not really how we use our tongue in speech or most of the time. And this approach actually does let you leave your tongue kind of in its natural resting position and move it around in your mouth. But you have to augment the tongue with something like a magnet, and you have to have sensors most likely on the outside of your mouth, possibly on the inside of your mouth. So we don't like that either.
Of the magnetic sensor.
What do you mean?
Just one single point?
Yeah, there's one magnet on the tongue. Is that what you mean?
Yeah.
Yeah. So the first thing that I thought of when we started working on this project is, well, mice work really, really well. Can't you just take the innards of a mouse and put them against, in the roof of your mouth, and then just move your tongue against the bottom of that mouse? And then you could just control anything that you can control with the mouse or use mouse input. So believe it or not, we actually tried that out. I took one of these little miniature mice and took it apart and stuck it in my mouth, and as well as convinced a few other of my colleagues like Johnny Lee to do the same. We played around with it a bunch, and it turns out that for a couple of different reasons, it doesn't track very well.
How big is the sensor here?
The sensor that's inside this is probably about less than a centimeter square footprint, and vertically maybe half a centimeter at most, something like that. So we just took the innards of this mouse, stuck it in our mouth, and it turns out our tongue, when you kind of press it against the bottom, well, first, if you don't put anything on the bottom of the mouse, it just has a big cavity there, which just starts to fill with saliva, so that doesn't do any good. So then you could try putting a piece of plastic down at the bottom of it where the focus point is for the mouse. But when you press your tongue up against that so that it's really flat, your tongue, at least for this mouse technology, becomes a little featureless. And so, as you can imagine, it's hard to track. Like if you take a mouse and you put it on glass or a surface like that, it's fairly featureless for that type of tracking technology. And then it's hard for it to track the movement of the mouse. So I thought, okay, well, I can solve that problem, at least temporarily. I'll just take some medical tape and wrap that around my tongue. Turns out that doesn't work really well either, and it tastes really bad. So this started to feel like maybe this whole tongue-computer interfaces wasn't a good idea. But then we had a small insight that actually panned out to be pretty good. And that was, instead of trying to use the technology of a mouse to look at the image of your tongue and then track how it's moving around, how about instead we use a much, much simpler version of that is just using the fact that your tongue reflects light, and then put multiple of those sensors in your mouth and trying to detect how your tongue's moving around that way, instead of trying to track it very precisely like you would with a mouse. So the basic idea here is that your mouth's pretty dark. It doesn't, as long as your mouth's closed, there's no other sources of infrared light in your mouth. Your tongue reflects infrared light pretty well, and there's this nice curve that light falls off in intensity over distance with some like square root function or something like that, or something close to that. And so what you can do is you can have an infrared emitter that bounces out and an infrared detector, and you can essentially detect how far away something is that's beneath your sensor. So this is used in industrial applications, in robotics, in a bunch of different places for just detecting like how close two things are together, and like detecting when you're about to close something or something like that. So we thought this technology actually can be done pretty small and can potentially be fabricated in a very small way. So why not try and put this in the mouth? So what we did, this is one of our early prototypes of the system, is we bought 4 commercial infrared proximity sensors that they use in industrial applications. These guys are pretty small. I can't remember the dimensions off the top of my head, but they have a profile of like 5 millimeters high, something like that. So they're not very big. And we went to an orthodontist and watched them take molds of somebody's mouth and make a retainer, and then opened, an orthodontic textbook on how to make a retainer, and bought all the supplies at UW, because UW has, when you say I'm at UW trying to buy orthodontic supplies, they just assume you're in the orthodontics department, so that's not a problem. And basically learned how to fabricate our own retainers. Now, these retainers that we were making aren't for correcting your teeth, so there's no like wire on the front of it or anything like that, and it's not like there's nothing like affixed to the individual teeth or anything like that. So this is just like the part of a retainer that fits up against your palate and then hooks around your molars. And so what we did is we got like a mold of our mouth and then poured a retainer. But in the process of pouring a retainer, we set down these infrared proximity sensors and ran some wires out the front of our mouth. A little uncomfortable to have a wire out the front of your mouth, but I'll address that in a little bit.
I have a question. So are those the sensors, are they like on the top of it, or are they inside?
Yeah, so I should have mentioned that. So these sensors are completely enclosed in the acrylic. So the idea is that you can essentially make all those sensors biocompatible, if you will, because the acrylic's biocompatible and the infrared light can be emitted and detected through the acrylic. There's actually a little bit of a complication there, because now you have an interface between. So normally when you have an infrared proximity sensor, you just have basically an air interface, right? You have your sensor and you have air, and then if you remember back to your physics and optics classes or whatever, you have emitter, and then you have air, and then you have something it's bouncing off of, but the only interface is that air to sensor interface. And so now you have sensor to acrylic to maybe saliva, and then some air, and then some saliva, and then it comes back again. So it's a little bit more, it doesn't work. Like if you take their performance curves and then we do the same match, which actually, for a little bit of an anecdote, if you're trying to assess the performance of how these work, we don't have really a lot of white space in here, unfortunately. But most of you are on this side of the room, so I'll write over here. Since you asked this question, I'm going to go off the path here for just a second. But one of the things that we did here is try to assess how well these sensors work for our situation. So can any of you guess how we would build a test harness for being able to produce like a graph of like voltage over distance or something like that for these sensors, and what the performance curve looks like? How you might build a test apparatus to simulate infrared proximity sensors in your mouth?
Did you get a cadaver tongue?
No. That's a good guess. Another guess might be to get a cow tongue. It's really easy to get a cow tongue. Yeah, I could try to use my dog. But you want it to be a really controlled situation. Actually, yeah, a cadaver tongue or a cow tongue might not be a bad way to do it. But we went cheaper than that. All right, so I won't hold you in suspense anymore. So what we did is we have a little platform here, and then we have an adjustable thing here, and then another platform, and then here's your infrared proximity sensor, right? That's sending out light and receiving it back. So what we do at the bottom here is, and we encase this sensor in acrylic, so you have the acrylic interface. And then what we put on the bottom is a piece of pepperoni. So we take pepperoni here, and then we put water on the pepperoni to simulate saliva, and then we put water on the acrylic right here. And then we can try to come up with a performance graph of what it looks like. And why this is useful is because there's a whole circuit behind this, and there's different ways that you can interpret the signal coming out of this, different ways you can modulate the infrared transmitter. And so you got to keep experimenting with this and figuring out what's going to work in this situation, because what you get off the data sheet from the manufacturer doesn't really address pepperoni or tongues or saliva or any of these situations. Yeah?
How does the local absorption of that radiation affect the proximity, the distance? If you use a really dark meat as opposed to really white meat, do you get a different? I
think you do get a little bit different absorption, but in everything that we did, the much bigger variable seemed to be the acrylic as well as the saliva.
Triangulation or an amplitude sensor?
Amplitude.
So it should vary quite a bit with contrast of the subject, right?
Oh, subject to subject? Yeah, it will vary. We do calibration per subject for that reason. So one of the problems here is that, I'll draw another version of this figure here. What this sensor really looks like is you have the transmitter and the receiver, and then you have some amount of acrylic, no matter what, right? Because we're trying to make this biocompatible. So you have some amount of acrylic, and then you have saliva or air or some combination right here. And so again, if you remember back to your physics classes, some of the light is going to go out like this and reflect off your tongue and come back. But some of the light is also going to reflect off this interface and come back, which is not good. That totally messes with your sensor, especially because the intensity of this is much more than the intensity of this. So we're trying to come up with a biocompatible way to do this. One of the first things we did was carve a notch in here and fill it with Sharpie ink, which worked pretty well, except for that we didn't really think it was a good idea to have like Sharpie ink in your mouth. So the thing we ended up doing, actually, which is kind of funny, is to carve a notch in the acrylic here and fill it with a compound of essentially acrylic and coffee, so that you can have like basically opaque dental acrylic in there. And then that does an okay job of isolating the transmitter and the receiver. All right, I diverged quite a bit. Yeah, go ahead.
So why can't you just embed it so it's like sticking out?
So because of the components of the infrared proximity sensor and detector have various properties like toxicity, we don't really want to have it in your mouth. So we need to have the acrylic there. I mean, for test purposes, we could have tried something like that, but we know eventually you can't do that.
Were there any triangulation sensors you could acquire that would eliminate that problem, like the sharp range sensors?
That's a good question. Like ultrasonic or
No, triangulation.
Triangulation with infrared. So based on timing.
No, just an off-axis illuminator, and depending on where it came back it's a position-sensitive detector. We can talk offline.
That's a good question. Yeah. I guess it depends a lot on how the tongue reflects the light, too.
And the short distance.
Yeah. I'm not sure if it'll work in that short a distance. Yeah. That's a good question. We should talk about it. I'm not sure if it'll work with how the tongue is reflecting light and how short the distance is, but that's a good question. It's worth trying. So, anyway, back to trying to figure out how to observe tongue movement in the mouth using this infrared proximity sensor problem that I described over there. So you have 4 of these, in our setup, we put 4 of these proximity sensors in this retainer that's in your mouth. So you can think of those as roughly kind of being overlaid on the tip of your tongue, or on the front of your teeth, on the left side of your teeth, the right side of your teeth, kind of near the front, and then one kind of over the middle of your palate. Do you have a question? Oh.
Yeah. So, what kind of time resolution do you have for this kind of measurement?
Like, what's the resolution?
The time. So, is it continuous measurement?
Yeah.
The time position?
Yeah. So, like, something like, I mean, you can. So the infrared proximity. Maybe I should have turned my phone off before I started giving a talk. Sorry about that. So you can, the infrared proximity sensors, the receivers and the transmitters, because they're like photodiode based, you can turn them on and off in like 6 nanoseconds or something like that. So you can modulate them very fast, and they react to the light really fast too. So it's just basically speed of light to your tongue and back, and they settle really, really quick. So it's more like the sampling rate we can do with our analog to digital converter and our microcontroller and stuff like that. So we sample it at like 250 hertz or something like that. But you could sample it even faster than that if you wanted to.
Like 10 milliseconds, 100. Okay, so that would be.
So like a couple milliseconds.
That's good.
Yeah. So that actually I don't think becomes too much of an issue. It's more the accuracy of when you get really close to the acrylic, you have these refraction issues. That stuff's much more of a concern than sampling rate. I'd say sampling rate's not a problem.
What time did you make measurement on in this case?
So that's what I'm going to describe. So we have these sensors in these 4 positions in the mouth. And so what we want to do is come up with some set of tongue movements that we can detect using those sensors so that we can then map those to some type of input. So in our work, what we mostly we tried a few different things, but what we mostly focused on was 4 different movements and a couple extras that I'll describe that we can detect somewhat robustly. And those are basically taking your tongue from its resting position, I'm using my hand here as a tongue, and swiping it. So from the rest position, do a swipe to the left in your mouth and then kind of returning to rest, or swiping your tongue to the right, so you can imagine just against your teeth, just left to right. Being able to tap your tongue against, sorry, they're down here, I'm blocking them. Tapping your tongue against the top of your mouth, or holding your tongue briefly against the top of your mouth. And so the way we detect it is actually a very simple heuristic, and that just requires a little calibration step, so no fancy machine learning or anything like that. And basically what we're looking at is the timing of when your tongue slides past these sensors. Depending on the shape of a person's mouth and how they move their tongue, the mapping of this can actually be backwards. So one of the things that's kind of interesting is that, again, I'll need the whiteboard. Can you guys see anything that I'm writing on the whiteboard over here? Okay, I'll erase this and use this far side again. So one of the things we learned when we started taking molds of people's mouths is people's mouth shapes are like wildly different, which I hadn't really thought about, but I guess makes sense. But like wildly different. Like some people's mouth cavities are really, really tiny, and some people's mouth cavities are really, really large. And some are really short, and some are really long. So people's mouth cavities are pretty different sizes, and so that affects how this problem works quite a bit. So in some people's mouths, when they swipe their tongue from left to right, the way these infrared proximity sensors detect that, so I'll overlay the sensors like this. In some people's mouths, you see the tongue kind of curve up and do a swiping against their teeth. And what you actually see is the back of the tongue getting close to this sensor and then getting close to this sensor. And in other people's mouths, you see the front of the tongue be on this side and then be on this side. So for some people, a left to right swipe looks like passing very close to the left sensor and the right sensor. And for some other people, it looks like right to left. What's good is that people tend to swipe their tongue the same way over and over again, or they can learn to. And so it's robust per person, but it can actually be totally backwards depending on who's doing the tongue swiping. Yeah.
How do you see all this stuff? I mean, how can you really get a good sense of what's going on inside people's mouths?
That's an excellent question. Things like, try that again and have your mouth open a little bit while I look in there. And then also kind of getting used to what the signal looks like while they're doing it over and over again. It actually is really hard. And in fact, I have a fixed retainer on the back of my teeth. And so it's not easy to take a mold of my mouth and not mess with that and build one of these retainers for myself. So I've actually never had this in my mouth before. So as a person trying to like design these interactions and figure out how it works, like, I built a retainer that like I use my finger on, and I have to like kind of come up with hypotheses about how somebody's tongue might work with that and like try it out and then watch somebody else do it. It's actually kind of a hard problem. It's a lot different from like watching somebody use a mouse or use a keyboard or use a game controller or a gestural interface or the muscle computer interface, all that stuff. Like you can kind of watch what's happening. This like you got to kind of infer it a little bit, and like you can watch a lot of and try and figure out what people are doing with their tongue in their mouth and whether they're actually following your directions, like externally, like looking at what's happening with their mouth and like the expression on their face, like while they're trying to do something. But yeah, it's a little funny. It's a good question.
So how natural it is when people maybe talk when this device is put in their mouth?
So the thicker the retainer is, the more it's going to become a problem with your speech. So if you have one of these retainers and it kind of, I'll have to draw another thing for you guys. So here's my poor drawing of what your teeth look like from like the top down. So if the retainer, and then from the side view, like you have teeth and then you have a palate to your mouth. if the retainer can occupy small a space this way as possible and can be as thin this way as possible, the more thin it is that way and the more you can have a little cut in right here, the more you can have your regular speech pattern or not really notice that it's in there when you're talking. If you make it really thick in either this direction or making this like a flat line or bulging out this way, it's harder to put your tongue in the normal positions that it's in when you're speaking. But to answer your question, you can talk with it in your mouth as long as it's kind of thin. The first couple we made were so thick that like you just have like saliva pouring out of your mouth the whole time. And but once we made it a little bit thinner, that wasn't so much of a problem anymore. You could ask Destiny about that. Yes.
So
and try to detect them robustly.
I mean, I don't know if you know much about speech. Well, I work on speech for years.
Oh, okay.
If you actually can measure the tongue tip, probably you won't be able to do that. And also 2 sensors in the tongue body and also lip. You can do recognition from that.
Yeah.
Just about 4 or 5 sensors.
Actually, that's a very interesting question and one that we've talked about a lot. And if you get some of that problem right and put a kind of a microarray of a bunch of those sensors in the retainer, I think you actually can do that. Especially if you modulate them. Because the photodiodes respond so fast, you can do some really cool stuff where you're turning on different ones at different times really fast and modulating it. I think that's totally possible.
In Europe, I think they're still selling the machine, but that was a magnetic sensor. They actually collect about 5 points in the month, including tape and then also the rhythm. Rhythm is very hard for you, in that case. And once you have that, you actually can do recognition.
Yeah, no, I think you actually can do it here too. Well, we didn't focus on that problem because you can't do it with these commercial sensors because they're too big essentially. But Babak Perviz, who's the EE professor, who I said at the beginning we worked on with this, he's like a nanofab guy, and so he's done a lot of really small LEDs like on contact lenses and stuff like that with self-assembly techniques onto all sorts of different substrates. And so it's a little bit harder on he's not sure how well that same technique will work for the infrared receiver, but he thinks it can work. So I think you can actually do a small array of many of these for really low cost. Yeah.
I think many years ago there was a retainer similar to that, well, with a fairly high granularity capacitive sensor array. And
oh, really?
For teaching kids who are deaf from birth where to put their tongue for speech.
Oh,
because that was one of the hardest things to convey, to teach kids is where to put their tongue.
We actually tried doing a capacitive thing. Initially, I didn't describe that in the early slides, but we definitely ran into the problem of capacitive and saliva, and we couldn't figure out a good solution to that problem. You had to dry it out a lot. But if you're willing to spend a couple of minutes, it works for a couple of minutes. And then you got to kind of dry it out again, and then it'll work for a couple of minutes. And so I don't know, maybe they came up with a better solution than we did.
A news story I saw on TV many years ago.
Okay, so maybe it only worked for a couple of minutes.
Any measurement for the lip movement, where the lip closes or open?
So in this version, we didn't mess with that at all because these sensors are all behind your teeth, in the center of your mouth. You could imagine with the corrective retainer actually has a wire that goes around your teeth. If you're doing the nanofabrication version and not these relatively big for inside your mouth sensors, it might be possible to look whether your mouth's open and whether your lip is eclipsing or not, and depending on how dense the array was, whether you could get some lip shape. I'm not sure, but it's possible. I think it'd be very interesting.
Maybe it's not bad. Once you get the tongue there, and then the camera can look at the lip.
Right.
You combine them all together, you can actually do recognition without having to speak. So in the meeting, you can actually talk about it.
Yeah, and another thing that
other people.
So there's a couple other things here that I didn't describe that we also looked into and tried a little bit. Since you're bringing it up, I'll stay on this slide for a little longer and describe what they are. So the other techniques that we started to mess with was one of them was putting a camera in the back of your mouth and like a quarter sphere mirror in the front of your mouth, and basically have these be really small, pointed from the back to the front to kind of look down back at your tongue and look at what's going on, and do it with infrared illumination and that kind of stuff for in your mouth. Some of the other things we talked about were taking a bundle optical fibers and pushing it into a camera in the back here, and then having those fibers space out and to kind of an arbitrary density all the way through the acrylic of the retainer. And it seemed like that would be a really good idea because there's a bunch of ways you could think about that as a sensor. If you had a bunch of infrared illuminators spaced in with it, an infrared filter, you could think of it as a really dense version of this, but you could also detect other things, like you can get image out of that. But we decided that that was going to be very difficult and expensive and hard for us to manufacture and test in a short period of time, so we kind of abandoned that route. But that's another approach that could potentially work even better than this and might be feasible. So the high-level point was that using these 4 sensors, you can get you can relatively easily get these 4 gestures in a robust way. There might be more you can do, but we wanted to look at least with what you could do with these 4. So I've already described this a little bit in words, but I'll just put it on a slide for a second. The basics of how this system works, this is our first prototype of it, is you have those proximity sensors in the retainer. The signal goes through an amplifier circuit that we have and an analog to digital converter, and then there's a microcontroller that's sampling that and then send it, in this case, over a serial port to a computer where we do the calibration and just the detection of the swipes, or whether you're tapping your tongue against the top of your mouth or holding it there.
So how weird is it to have the wire coming in your mouth?
It's weird. In fact, it's hard to talk with the wire coming out of the front of your mouth. It also tends to cause a fair amount of drooling, which Desney claims is uncomfortable. I don't know. I've never tried the thing before. He might just be a complainer.
So I'm speaking to a wireless information sensor implementing.
Yeah, I'll talk about that in a minute. This is just the first prototype. I thought I'd show it to you. So I already drew or showed this curve in my hands and talked about some of these problems that I drew out on the board. But here's a figure. I think this figure is actually from their data sheet. But you have an LED transmitting stuff out. It comes back in, photodiode. And the way this sensor works is you essentially get a voltage that's dependent on how much light's reflected back in, and assuming a somewhat constant setup, the amount of light that's reflected back is dependent on the distance it is away. And this is kind of what that curve looks like with voltage over distance. So as you would guess, the farther away you get, the less light that's reflected back. So the closer these dots get together, the farther you are out, the less sensitivity you have about whether it's 25 millimeters or 26 millimeters. Whereas when you get really close, that change in intensity with how this curve works, you can actually tell those apart pretty well. The one caveat here that you'll notice that looks kind of funny is this curve doesn't start here and go down. The curve starts here and goes up and then comes back down. So there's this bump. So when you're really close to the sensor, it's hard to tell whether you're like 1 millimeter away or 5 millimeters away. And part of that is because when you get really close to the sensor, how much light's reflecting back.
I noticed, at least schematically, it looks like the sensors and the LED are domed on the top, giving it some optical properties. And if you fill that in with acrylic, doesn't that change the optical properties of the luminance?
Yeah. And so we tried to like push this curve as far this way as we can by doing things like that, by filling it with acrylic, with putting the coffee or the Sharpie in between, and so that the first place you can have crosstalk is up here instead of here and stuff like that. And we're able to push this curve around a little bit, which is good. And I was trying to remember, we actually have a clever technique for being able to tell which side of this curve you're on, but I can't remember what that technique was now. I came up with it too, and I can't remember. But there's actually a couple of neat little tricks that we came up with so that you can actually have a different way of looking at this also to figure out which side of the curve you're on. Wish I could remember what that was because it was clever. But anyway, so fabrication, I talked about it before. You take a mold of your mouth, and then you make a mold from that, and then you lay out your parts on that mold, and then you mix acrylic and pour it in there, and it hardens, and you have a retainer. This is one of the many iterations that only had 2 proximity sensors. So what's the first application that you would try with this? Well, first you convince Dan to put it in his mouth, and then you ask him to play Tetris with it. Or at least that's my approach to research problems, is get Dan to try it out and get him to try and play Tetris. So Tetris obviously isn't the main application of tongue-computer interfaces, but this will show you kind of how fast he can make gestures and have them be recognized and how accurately. So what he's doing is swiping his tongue to the left to move a piece left, swiping his tongue to the right to move a piece right, tapping his tongue against the top of his mouth to rotate the piece, and then he's holding it there for a second to make the piece drop down. So in normal Tetris, that might be left, right, up, and down, or something like that. So kind of a directional pad map to those 4 things that we could detect. But the thing that we did after that, which I think is actually a lot more interesting, is trying to map those same controls to the control of a motorized chair. So what we did was grab the motorized chair, built an interface to control its direction. We actually talked to the manufacturer of the control unit for this chair, and they were actually super helpful. They thought our project was cool, and they spent time with us on the phone and sent us a bunch of debugging hardware so we could reprogram the chair and do all sorts of stuff. They're they're like, yeah, as long as you send it back, it's fine with us. And so they sent us all their hardware. They're actually really helpful. It was a really positive experience, actually. And so we built an interface for controlling it just to hook up to the computer. And then we came up with a slightly different way of using those 4 sensors to control the chair. So to turn the chair to the left, you swipe your tongue left to begin turning the chair, but then you just hold your tongue on the left side of your mouth while you want the chair to continue turning, and then just drop your tongue back to a rest position to stop. And same thing for going right. You swipe your tongue right, the chair starts to turn, and then when you put your tongue back in a rest position, the chair stops, and that's your new heading. The way that we were controlling the chair, the software interface, would only let us either drive the chair forward, backward, or turn one direction or the other. So we can't do nice sweeping curves like that. We can only go forward, stop, turn, go forward, stop, turn, go backward, that kind of thing. And then when we're going forward, what we do is we hold the tongue at the top of the mouth. So that's your accelerator. You kind of hit the gas and then it starts to move. But then once it starts moving, because those infrared proximity sensors have that nice little curve, we can use them not just as a binary whether the tongue is near the sensor, but also how far away. And so we control the speed of the chair by how high your tongue is in your mouth. So you can kind of move the tongue up and down to kind of speed up and then slow down and then speed up again as you're moving forward. So usually you would just kind of speed up, go fast, and then gracefully slow down. But you can do different things that way. And then if you, for example, steer and turn, and then you're trying to go this way, and you clip this chair, and so you're kind of stuck against that chair, what we did is we used that tap against the top of your mouth to make the chair just back off by a foot, and then you can turn and go forward again. So how do you test this kind of thing out? Well, we just went out here in front of the building and set up a little obstacle course with these chairs here, and formed a little route to just go through the chairs like that and just see how fast we can do it and how it compared to controlling the chair normally or controlling it with the keyboard, just as a way to kind of ballpark if this interface is kind of feasible at all. Dan was tired of my interfaces, so I had to convince Desney to do it this time. So this is Desney controlling the chair with his tongue. He's got a laptop in his lap that has a kill switch, which needed to be used occasionally. But other than that, he's just controlling it with his tongue here. So swiping his tongue, initiating a turn, then stop it, and then returning his tongue to rest to stop the turn, and then moving forward. So he'll execute another turn, and then straight, and then another turn, and then come through the finish line here.
To stop, he just have to relax.
Yeah, just has to relax.
To go back to the neutral position.
And while it's in his mouth, he can actually sit there and talk to you, and nothing happens. Because if you think about how those work, you have to swipe and hold to start a turn left, swipe right, or the only thing that you really have to be worried about is tap, something being interpreted as a tap on the top of your mouth and having it back up a little. But for the most part, you can talk with it in your mouth and nothing really happens. I think really you want to have a more robust way of turning the system on and off with your tongue or with voice or something like that. And another thing that people ask about with this is, but what about in an emergency situation? Something runs in front of you, and the infrared proximity sensors are never going to be perfect. And what do you do in that situation? And my answer actually is that I think you go back and you borrow a little bit from those other interfaces that we didn't like, and you just put a physical button on the top of that retainer. So you don't want to be manipulating a physical button all the time, like curling your tongue back and pressing up, because it's uncomfortable over time. But that doesn't mean you can't have a kill switch that's a physical button and use that in combination with the infrared proximity sensors that are doing most of the control. So as you alluded to, it's not necessarily comfortable to have a wire hanging out the front of your mouth. So this was actually the first version of us building a wireless version of this. So putting the radio, the microcontroller, and everything in one retainer. You can see it fits in his mouth. That version is a little bit thick, so it impedes his speech a fair amount. But it works, which is kind of cool. And then this is the second version where we ran our own boards. So here's the main microcontroller and radio chip, and then we have the antenna out here on another board and some power stuff on that board and the battery over here. So we were able to split it apart and kind of form it in there. These are all fairly rigid PCBs and stuff like that, so you could actually make this stuff smaller. You could also put a lot of this stuff into your own custom silicon if you wanted to and make it smaller and fit in there. One of the bigger problems, and you can make, like I said before, you can nanofabricate most of the components of these sensors and make them pretty small. One of the biggest problems I would say is it's hard to make the battery smaller. So this is a lithium polymer battery, but you can run this. I think that if you're doing most of the processing on board and you're only transmitting off the commands wirelessly, you can actually make this thing run for a day on a battery that would fit in the retainer. But what we were doing in our debug setup is just blasting the sensor data that's sampled at a high rate the whole time. And when you do that, a battery this size is only going to last like an hour or something like that.
So can you change the battery from something to something?
So what we did, we had a couple of different methods for doing that. The easiest one was to use these two metal hooks to recharge the battery. You could.
That seems non-invasive.
Yes. I mean, this isn't really that invasive either, but you would do induction, I think, in a commercial product.
For this particular application, since you only need to detect these 4 gestures, you really don't need to sample that fast, right?
Right.
Maybe every 20 hertz probably.
Or yeah.
That would save a little better.
Yeah, maybe something like 30 hertz or something like that. It kind of depends on, you got to catch if you're swiping your tongue fast and you're trying to catch the timing robustly of which one it swiped past first in that situation, and then you're just detecting that it's held over there, you have to be sampling pretty fast for that tongue swipe. But I don't think that that's the main power problem. I mean, the radio, using the radio is like an order of magnitude more power than like doing a couple additions on the microcontroller, like sampling, yeah. So I think you can make this run for a day. I think it might be hard to push it beyond that, but you can make it run for a day. I don't think that's a problem. So I think that's everything that I have. Here's a little summary slide. But basically, kind of the future directions are looking at whether you can use that array of sensors, make them a little bit smaller, add a few more, and expand that gesture set, maybe double it, so that you can maybe, for applications like controlling the motorized chair, be able to do a little bit more and a little bit more robustly. So also be able to control like the tilt functions or have a nice mode switch for going between driving the chair and doing the tilt functions and stuff like that. As well as I think that it could also be useful for there's a bunch of different standards out there for how you can do remote control of like doors and elevators and stuff like that for people who are in motorized chairs. And you can imagine having a mode switching way and being able to use the same interface to control those things too. So you drive your motorized chair and you come up to an elevator and you need to control it. And if you don't have any motor control, you can't tap the button. Some people who are quadriplegic do have some motor control, and so they can still do things like operate an elevator. But a lot of people can't. So, yeah.
Comparing bandwidth for HCI uses to say sip and puff or a wood stick.
That's a good question. We haven't tried to like do things like figure out how many bits each of those have. And what we were mostly trying to address is kind of like a comfort thing. So from experience, I've spent a little bit of time in rehab hospitals for people who have just suffered like a spinal injury and become quadriplegic. And sip and puff control of a computer or a motorized chair, just anecdotally, is a lot slower learning process than the tongue retainer. In the tongue retainer, people in our study, we did a study with like just 4 people from around the office. They could all play Tetris in about 5 minutes. And people trying to do the same thing with the sip and puff, because the sip and puff, to get 4 controls, it's 2 levels of negative pressure and 2 levels of positive pressure. And like it's really hard to control that. The other thing that's really bad about it is that people who have had spinal injuries, I think it's way more than half have much more limited than an able-bodied person respiratory ability. And so sip and puff switches are kind of tough from that standpoint, especially early on when they're trying to learn it right after, while they're still in the hospital, still having rehab from the injury. Their lung capacity tends to be very just diminished, so it's hard to do that. And they're trying to like talk to you and try that, and yeah, sip and puff is tough from that. And wood stick can be good also, but you have to have both of those require augmentation right in front of you and stuff. One of the things that's really cool about this actually is that it's totally inside your mouth, and if you make it thin enough, it doesn't really get in the way of your speech. And sip and puff and the stick, like you have to have them out in front. It's just one more thing when you're already sitting in a motorized chair, right? It's one more thing that's between you and the people that you're interacting with.
Dignity factor was huge.
Yeah.
They would put that almost the highest priority.
Exactly. So that's been my experience in talking with people. Yeah.
Is there any, somewhat reminiscent of the voice draw, where you have like continuous motion?
Yeah.
Do that with these.
Yeah, we only have like one little piece of continuous in the control of the speed.
Speed.
Yeah, I think that as you have a bigger array of those, so that there's more parts of the mouth where you can try to do things like control the tongue shape. Like you use it analog in speech all the time, right? Like you do, that's how you talk. I think there actually are a bunch of opportunities for that, and especially not for a motorized chair, but like for interaction, for doing things on a computer. That's the place where I think you'd really have to leverage the analog ability to have interesting and useful controls of applications. I'm not sure how much you need it for the motorized chair beyond a couple of different things like speed. But.
Has there,
Go ahead.
thanks. Has there been any studies about just how tired the tongue gets over time?
That's a good question. So no, not that we know of, not for this kind of stuff. That's something that we're really interested in though, because it really impacts your ability to use it. We talked to a few different people, like speech pathologists and a few other physicians, and kind of their response was that your tongue's a muscle, you should be able to build up some endurance and stuff like that, and like you should be able to operate a device like this, but I don't really know whether that's true or not.
Yeah. I'm sure you can, but it's also used for other purposes.
Right. So I don't know the answer to that question.
So I'm just trying to think about whether there's a way of detecting tongue tip position, whether tongue tip actually get touched on the palace or any part of the.
I think if you had an array of like 100 emitter detectors with analog distance,
that would detect the whole shape.
Yeah.
See, so this is a very quick just point. This is get 4 sensors that can only detect this gross movement.
Yeah,
not
exactly.
any fine movement.
Well, you can detect fine movement. It's just it can't detect things like shape very easily. If you have, when you have a big array of sensors that you're sampling really fast, so you're alternating which one you have turned on at each time, like which emitter. Also, you don't have to have a one-to-one pairing of emitters and transmitters. So you might have an emitter on somewhere in your array, and then you might, at that same time, sample 12 different detectors, and then you might move the emitter over to another emitter that's just a little ways away, and then sample a whole bunch of detectors again, and then you can take all of those different signals that you're sampling, right, and like take average Gaussian. Like there's all sorts of tricks you could use then to try to have a smoother, more accurate version of the shape of the tongue and the movement, and maybe get a better shape path and stuff like that. But with 4 sensors, you can't really do any of those tricks.
And also this sensor goes to only one direction, right? So it actually doesn't detect particular part of the tongue. Rather, it just detect whatever is something there.
So yeah, so well, and how far
So
away
if
it
I'm
is.
moving the tongue like this, you actually detect different part of the tongue, not just a fixed part of the tongue.
Yeah.
That's not. Yeah.
So when you think of it as being one emitter and one detector, that's true. But in the scenario I was just describing, where you have a variety of emitters and a variety of detectors, and you're turning on different ones at different times, now you're actually getting a much more global look at what that tongue position looks like. So imagine, like, if you will, like when you take a camera and you point it at something and you do like an edge detector or something like that, and you see those lines kind of move around, or if you take like a Kinect camera and you take the depth output or something like that. Like a Kinect camera has what? What's the depth thing? Like 320 by 240 or something like that? Yeah, at like 30 hertz maybe, if you will, and it has a fairly decent amount of error, right? If you did an array of infrared proximity emitter detectors, and they don't have to be paired up, you could get something that kind of approximates that in the mouth, and you can see how you might be able to do tongue shape that way. We haven't tried that, so I don't know if it would actually work, but.
Or resistant touchpad. You could do that.
Yeah.
Resistant touchpad.
Yeah, for when you're in contact. Yeah, when you're in contact. So actually, I think pairing up things like resistive touchpad plus this, plus a couple of like physical buttons as a kill switch and stuff like that, then you would start to have a really complete package of interaction possibilities, all in a retainer wirelessly in the mouth. Which I think that then you start to be able to get to a really, really high bandwidth device that's much higher than all those technologies I showed at the beginning, with the exception of obviously speech. I would think of this technology as being complementary to speech, right? You would just use it in different situations. So, but everything else besides speech from the beginning one is pretty low bandwidth, and this could be a lot higher bandwidth.
So any way to detect the villi opening or closing, and that's one of the extremely important feature for speech. I don't know.
In the back of your mouth?
Yeah, in the back of, right behind the palate. So
Yeah. That's a good question.
it's a kind of soft tissue there, so it's closed or open.
I mean, yeah, I think you could. I mean, the right set of either cameras, infrared detect. So you can. How far back is that from the front of your mouth?
It's opening, right? Well,
Yeah, no. How far back is the opening?
That was already quite bad.
Because the farther back it is, in some ways, if there's a direct line, the easier the sensing problem is.
Easier or more difficult? If it's further back, then you can just put in there because.
If it's a straight line, I don't know if it's a straight line or not. If it's line of sight, then sight, if you will. When you move beyond a few centimeters, a lot of these sensing problems get a little bit easier because a lot of them have a bunch of interference problems when you're close up. So you might be able to even use things like. I don't think I'd put ultrasonic in there, but it's possible that it would be useful. It's hard to use ultrasonic really close, but when you get a little bit of a distance, you can.
Elif, who makes the jawbone sensor, started their technology by using an ultrasonic imaging device they hold up to the throat, and it would actually image the throat cavity for speech.
Altogether, it's available. That kind of
Yeah,
sensor.
and then they would use the volume feedback to modulate
Okay.
various oscillators to try to synthesize speech.
Okay. So include entire tongue shape. Oh, right. Does it measure entire
No,
tongue shape?
throat
Oh,
cavity.
the throat. Okay.
Cavity.
So how?
Yeah, but it tries to image the parts of the throat that
I see that. Yeah, that's the source.
affect speech, and then they use that metric for modulating whatever to synthesize speech.
Oh. Okay. So it's already done there.
Thank you, Scott.
Yeah, you bet. And if you guys are patient, I will run up to my office and run back down, and you guys can actually see what these physical prototypes look like.